we're going to be working on the inverse trig functions, okay? If you do have that little sheet that has the 3 graphs at the bottom, you're going to want to get that out, and you can probably take most of your notes between that little sheet, probably on that sheet, and maybe just a little bit on a notebook paper of some application for it, okay? But for the most part, we're going to start with the graphs. Now let's just talk about inverse, first of all. What is an inverse from any math inverse when we did this before? Come on, guys. What's an inverse? All right, very good. It's when you switch x and y. This is the same thing. And we're trying to apply this concept of switching the x and y, or switching the independent and dependent variable, but with a trig function, all right? So if we wanted to do, let's say we want to start with sines. Well, what we're doing is we are taking the graph or the function y equals sine x, and we are switching the x and y. So algebraically, it would look like this, just like we used to do in the past. But then the goal, remember, is to isolate y. So it becomes a question of like, well, okay, how do I get that y out from behind a sign? And you guys, you can't just divide off the word sine. It doesn't work that way, because if I tried this, it's like this doesn't make sense, because when you have a sine, cosine, or tangent, you're supposed to have something behind it. It makes no sense without an angle behind it. So what that means is there has to be a different kind of algebra to undo what you see here. And the way that you undo it is by applying its inverse function to both sides. So basically it's going to look something like this. In order to get this word off of y, we are going to take the sine inverse of this entire equation. So we are applying an inverse function right off the bat. And this is just a different type of math is what this is, and the purpose of it is to undo what you see. So when I distribute this or apply this to both sides, what ends up happening is over here you have sine inverse of x, and the sine inverse and the sine are side by side, and guess what happens? What do you think happens over here when an inverse gets with its person and they're side by side like that? They just cancel out. You know what it's the same as? It's the same as when y'all do this kind of thing. You know what I'm saying? When y'all put a square on a square root, you're applying inverse functions to each other, and what does it do? Cancels the symbol out. This is the same idea. So those are gone. So the inverse of y equals sine x is y equals sine inverse x after you go through the rigmarole, okay? This is that button on the calculator. This is the button that some of y'all tried to use when we were doing like secant and cosecant and cotangent, and I was like, no, don't push that. It's a whole different thing. It is a whole different thing, because secant, cosecant, and cotangent are reciprocals. And then sine inverse, cosine inverse, and tangent inverse are literal inverse functions. And it is, graphically it'll be totally different, because we are switching the x and the y. Now before I get into the actual graph, just so y'all know, a fancier way to write this, or not really fancier, but a more better way is to do this. These are sometimes called the arc functions, arc sine, arc cosine, arc tangent. A lot of people in higher level mathematics do this and think it's superior. I am one of them. Because guys, I don't like having a weird -1 nested on my function like that. Because yeah, it does mean inverse, and that's what y'all learned in Algebra 2. But sometimes this can be mistaken for an exponent. And people think, like when you have a negative exponent, what does that tell you to do? A reciprocal. So see how the worlds are kind of intertwined, and it makes it scary. So it's like, I don't want you to mess that up. So you can write it either way, and you're going to be correct. Just make sure you have that -1 in the correct spot. Make sure it's between the word and the variable, or you'll see me calling it an arc sine instead. But they mean the same thing. So we're going to take our x and y axis that we normally have, and we are going to switch them, because that's what an inverse says to do, right? X becomes y, y becomes x. So normally on the x-axis we have pi over 2, pi, 3 pi over 2, 2 pi, right? That's what we normally have. Not no mo. Those are now going to go here. And I know I ran out of room because I'm not planning ahead. But in theory, yeah, we would just, we'd keep trucking up this way with our pi over 2, pi, 3 pi over 2, 2 pi. And now, what kind of scale does our x-axis get? There you go, 1, 2, 3, -1, -2, like that. So those switch. And so basically, whenever you are doing this, it's almost like when something's here, what you're going to see in this spot right there, those are what's usually our output, okay? So the numbers that get plugged in here are the sign values that you guys know from around the circle. So what are some of the y values from around the circle that are going to become our x's? 1/2, that's a good one. We see that a lot. Root what? Root 2 over 2, root 3 over 2, 1, 0, and then the negatives. Okay, so all of those, it's like those become your inputs. Your outputs are now what? What's your y-axis now? What's your y-axis? What's on your y-axis? Yeah, and those are not your sine values. Those are your radians or your angles. So those switch spots. Your angles become the y. Your answers in retrospect become the x's. So they change places. So when you see a problem like this, and you're making a chart, and you're inputting something like that, y is equal to the arc sine of 1, then what your brain should be saying is, what angle has a y value? Since it's the word sine, we need to think about y values. What angle has a y value of 1? That's what our brain needs to be thinking when we see it written like this, okay? So where does that happen? Where do we have a y value of 1? Okay, so what I would do to graph that point is now this 1 is my input, right? It's my x. So I go over 1 and up to pi over 2. So now we're creating a graph the other way. What about, let's do 0, okay? Where on the circle, if I want to change this, let's do eraser real quick. Okay, let me change that. And if I change that to like a 0, then I'm saying what angle on the circle has a y value of 0? So where does that happen? Well, it happens at 0. Good. Where else does it happen? Good. It also happens at pi and 2 pi. So I could go up here, wherever that's going to be, somewhere up here. Okay. And if I go in the negative direction, then it's going to happen at negative pi and negative 2 pi and all these other things. Let's do one more key one, and then we'll start talking about cleaning this up. How about negative 1? I don't want to do the fraction ones. Like we could, but ooh. I'm not excited about that. So let's do negative 1. So what angle has a y value of negative 1? Good. Negative pi over 2 would have 1, and that would be negative 1, negative pi over 2. Anywhere else? No, 3 pi over 2. So if we had kept this going up top, then it would be 1 right up here too. So if we started to connect the dots between red and blue and red and blue, and oh my gosh, look at what's happening. Some of y'all might have already sort of deduced that that was going to happen because we are taking the graph of cosine and doing its inverse. And we learned how to do that graphically back in the day, right? Remember, an inverse is not just switching x and y. It's a reflection over what line? Very good. Good memory. So if we took the graph of cosine, reflected it over the line y equals x, which is that diagonal, it would now look like this. All right? Now we need to clean it up. Because why is this problematic? It's not even a function. And we're sitting here calling them the inverse trig functions, but this ain't even a function. So what the math world decided to do is just restrict the domain. They restricted the domain of the original function so that when it's reflected, it'll look legit, okay? So let's do some restricting. Where does your I go as that would be a good place to cut it off. You know what I mean? Does anyone see a good little range of this graph that they would like to chop it at? Okay, at 1. But we're probably going to have to look at the y-axis because the 1's hit in a bunch of places. So, like for instance, could I go maybe 0 to pi? Would that be okay? No. Why would that? Y'all see how that would be bad because it would still be not a function? Okay, so let's look for a core part of the graph that would look good. Who's got it? Yell it out. Yep, that's what I would choose. Whee! And it's not just what would I choose or what would you choose. We don't get a choice really. This is what the math world shows. It does seem to make the most sense to choose that little window because it's right around the origin. It makes us feel good. And then everything else starts to recopy. This black graph from here to here is the graph of sine inverse. And this is what should go on your notes paper. So what questions do we have over anything that's happened so far before we talk about what you're going to do with that? Okay, so does this thing ask you things like domain, range, and all that? Okay, cool. So we can do domain and range. So when we do domain and range, we are doing it for the black graph. We don't have to go back to the original and think backwards and all that crap. Okay, just take a look at this one. The range of this, we just said, negative pi over 2 to pi over 2. There's your range. What about your domain? Negative 1 to 1. So it's really that easy. You're just doing the little domain, the little range. Make sure you use brackets because it is, it lands on those spots. Does it ask anything else besides that? Okay. Now, here's what I want you to do under that graph. I'll explain later what the purpose is, but it's good to have it all in one place. Under the arcsine graph, do you have room to do a baby little, just a little x and y axis? Baby x and y axis. I hope you do. If so, I want you to draw a baby unit circle on that baby x and y axis, just a tiny circle. And what we want to do is be able to correlate what we see here back to the unit circle in terms of a domain or a range. So if this graph only exists between negative pi over 2 and pi over 2, okay, what part of the circle is that? What quadrants of the circle is that? Okay, I see your finger up in the air as a 1, and I like that. Yes, definitely quadrant 1, because 0 to pi over 2 would be quadrant 1. What about negative pi over 2 to 0? Where's that located? Very good. That one is like, remember negative angles just mean you go backwards, right? So where's negative pi over 2? Right there. So this also needs to be shaded. Like I said, I'll talk about the purpose of the shading in just a second, but we're going to do this with all of our graphs so that we can relate the inverse back to the circle, and then when we apply it in a minute, it'll be like pretty easy. All right, the next one, I'm not going to go into all the hoopla for, I'm just going to draw them because it's established the same way. I just don't want to go through all that again unless y'all have a question. So let's do arc sine. No, I already did that, silly. Arc cosine and arc tangent. It's going to be the same idea in terms of I know my axis is going to be the same, like 1, 2, negative 1, negative 2, pi over 2, pi, negative pi over 2. Okay, my scale is pretty atrocious here. But that's what we're doing, okay? So hopefully that's already on there, and if not, y'all need to label it on there. And so with arc cosine, what happens is it gets restricted in a different place, because remember that wave starts in a different place. It's still going to look like a wave. It's still going to be vertical, but it gets cut off a little bit differently. This one I always go dyslexic on. So I remember thinking 180, 180 is -1. And I know that 0 is +1, and I know, okay, so it's this. That's where the world chooses to restrict cosine, is between those two. Same thing as before, it's because it looks good. It's close to the origin, but if we kept going, we would fail the function test, the vertical line test. Arctangent is kind of interesting. We only want one wave of tangent to repeat. And if you look at your normal tangent graph and imagine reflecting it across the line y = x, I think what you're about to see is going to make perfect sense. The asymptotes are now going to be horizontal. They used to be vertical, now they're horizontal because x becomes y becomes x. The graph used to be looking like x to the third, but here's what's cool about this. Who remembers the inverse of x to the third? The cube root of x. Y'all remember the shape of cube root of x? It was one of our parents in the fall. It was this. And so since the parent for tangent kind of looked like that, then the inverse kind of looks like that. The only difference is the asymptotes that are there. Okay? So that's going to be your tangent graph. So same thing that we did before. Underneath, let's draw our baby unit circles, and let's start sketching the restrictions. Okay. So where would cosine be restricted to in terms of quadrants? If you're looking at your angles. Remember, you're using your y-axis right now to figure this out. Quadrant 1 and 2. Your angles can go from 0 to pi. So 0 to pi is going to happen up here. So on arc cosine, that should be our picture. Arc tangent is going from -pi/2 to +pi/2. So what quadrants are those? Okay, good. Just like sine, it's going to be 1 and 4. Now, if you want to extend this even further on your note sheet and write another little note, how do I say this without sounding confusing? Okay. The reciprocals of the inverse functions are also going to share the same restrictions on their graph. In other words, okay, who does secant go with? Secant's the reciprocal of cosine. So right here, if somebody were to ask you about arc secant, you would also use that picture, okay? Would you use the same graph? Heck no, it's a totally different graph, but good news to y'all, we don't care about those graphs right now. In fact, even in college, my professors were like, we don't care about those graphs. You're never going to, use them, okay? Arctangent, well, that would mean that arc what is going to be the same? What's the reciprocal of tangent? This is the easy one. Who goes with tangent? Cotangent, there we go. So if I asked you about our cotangent of x, it's also going to use the same picture of this. So which one's left that you can fill in that goes with sine? Cosecant, good. So arc cosecant, you do need to fill in on the arc sine one, just under it, just to say, we're just showing that they share that same picture there, not that they share the same thing here, okay? So take a second while I set up this next little, what are we going to do with this, and fill in, if you haven't already, the domain and range of all three of those on your sheet. Ask me if you have questions. Check with a neighbor to make sure you got them right. So the whole purpose of looking at these inverse graphs and seeing where they live, where they're residing, is so that we can answer questions like this. We can do trig backwards now, is the one way to think about it. We are not going to be doing transformations of those parents. Don't think we're going to be moving them around and stuff like that. It's not about that. It's just establishing the graph so you can establish the unit circle and where you live so that you can answer a question like this. It's as simple as that. This is what we've been doing for 3 weeks. I ask you this, you tell me the answer. So what is the answer? The sine of pi over 6 is 1/2. Oh, I goofed on this. I goofed. No, I was right. Sorry, I'm getting myself all tricky. So, it would look more like this, okay? That was right, it would look like this. Okay, so it's like this. So we would say the sine of pi over 6 is 1/2. So then if somebody said arc sine of blank equals pi over 6, you're working backwards to say, oh, well, that's going to be a 1/2. What I would actually do is not give you this, and I would actually give it to you like this and leave that blank is what I would do, okay? I just wanted you to see that these are just switching places is what's happening, but this is how the problem will be given, is like that instead. And yes, you would answer pi over 6, because what needs to happen in your brain is you need to be able to say, as soon as you see this side, your brain should think, what angle? These are always angle questions. What angle has a sine value or a y value of 1/2? And on the unit circle, this is why we did what we did just a second ago. There's actually 2 spots on the unit circle, guys, where this happens. There's 2 spots. Where's the other spot where this happens? So a y value of 1/2. It happens here, and where else? Down here, or, oh yeah, here we go. So really it happens in 2 spots. The reason we're not going to pick 5 pi over 6 is because of the shading that you just did on your paper. When we did sine, we said that arc sine has to be from these 2 quadrants only. So when I give my answer, I'm only going to give that answer. Does this make sense? So even though it shows up more than once, we're only going to give it from there. Okay, so keep that in mind. Okay, so let's do a couple more examples along these same lines. In fact, I will shut up and just see how you do with using your circle and figuring that out. Bell's about to ring. Okay, so. Alright, so for the sake of time, I actually can't give you that long. I said I would give you time, but the bell's going to ring soon. So the arc cosine of negative root 3 over 2. Your brain, in a sentence, should be thinking what? Good. The angle that has a, what is cosine? X. What angle has an X value of negative root 3 over 2? And you're thinking backwards from your unit circle. So where did the negative x's of root 3 over 2 happen? That's going to be in quadrants 2 and 3. And since we're going to be in quadrants 2 and 3, which one am I going to have? The second quadrant one or the third quadrant one?
Second.
Good. Because of the shading that we did a second ago. So only give me the 5 pi over 6 is the answer. The next one is tangent. Arctangent of 1. Okay, well the 1s happen at all the 45 degrees all over the circle. Some are positive, some are negative, depending on the quadrant. Does anybody know which ones are the positive ones? Where that happens? Besides quadrant 1. Like quadrant 1, everything is positive. But where's the other positive tangent one happening? Very good, because you're doing a negative divided by a negative. Remember, tangent is your y over your x. So you're asking what angle has a y over x that's equal to 1. So it's either quadrant 1 or quadrant 3. Which one's it going to be? 1, because of the shading that we did, pi over 4. And we'll do more examples tomorrow where they get a little bit trickier, to be continued, but that is essentially inverse functions.